Now I'm going to show you how to do how to calculate confidence intervals for the average and for variance, for standard deviation in R. And I'm going to use the same example that I used in the lecture. It's 2 rivers, Ribe and Wade. And then we took 10 glasses of water from each and estimated how much of chloride in each glass. So you can find file in Moodle or in EDX Learn. The file is called river CSV. So first of all, I will load the file. Because it's this CSV file has these Danish standards with semicolon as a value separator and comma as a decimal separator. I use CSV2 here to make my life a little bit easier. And I think I forgot to set it as working directory. So now I can get the data. And I have header, I don't have any row name, so that's enough. Then I will show the data on the screen. Okay. So that's the data. We have a data frame with two columns, one for Wade, one for Ribe. And then, yeah, let's do something. Okay, let's start with simple things. We can just calculate summary for the data and see the quartiles, quantiles, as well as the average values. And then you can see that the average values are exactly what we had before. Okay, what we had in this lecture. Now I'm going to calculate means. I will just use it like this. First, I calculate mean for Wade, and then I do the same for Ribe and combine them together. Mean data $Ribe, then show the average values. Okay, so that's the average values: 152.15 and 139.26 milligrams per liter. Okay. We can calculate the standard deviation using similar way. The function is SD data Wade, then SD data Ribe, and show the standard deviation. Okay. So that's okay. I think I made a typo. So this is the standard deviation. You see, in each case we have about 9.3, 9.9, so it's about 10. Okay. Well, let's make a cuckoo plot and see do we really have normally distributed values. Otherwise we can't use t-distribution because we have less than 30 values, right? So let's start with cuckoo plot. I will use this MF row to split my plotting data into two. So cuckoo norm, first of all it's Wade, then the same with cuckoo line. So we get the theoretical line for them. And then I'll just copy and paste to get this for Ribe. Okay, Ribe, and one more. Okay, I'll keep the standard color. So this is the cuckoo plot. You can see that for Wade, the plot looks the data looks very normal, right? So the points are pretty close to this theoretical line. For Ribe, we have two sort of outliers here. So two values which seems to be a little bit extreme. So let's make a test and see if indeed we can use the normality for. If indeed we can assume that the values are normally distributed. Okay, so again for Wade, it will be Shapiro test, data Wade. Then I will just show the values of the test. Okay, so you see that. Let me see R1. So you see that the p-value is 0.99. Okay, so I mean we don't have any doubts. Our null hypothesis is that it's normally distributed values. The population is normally distributed, and then this is the chance to get the sample like we have, or even worse, if indeed it came from normally distributed population. So the p-value is very high. Okay, so we don't have any doubts here. Now we can do the same for Ribe and see if we can use normality assumption about Ribe. Show R2. Then you see this is the p-value for Ribe. It's smaller, but it's still pretty large, pretty high. Okay, so we can use the normality assumption for Ribe. Okay. Then just to make it the preliminary comparison, we can compare these two sets of values using a box plot. I will get back to default layout for the graphics and then make a box plot for the reverse. So you can see this is the box plot, this is for VADA, this is for RIBA, and we see that there is a difference. At least the box plot shows us that there is a difference, but we don't know yet, is it significant, is it a real difference, not just by chance. Okay, so that's why we need to calculate the intervals, and then in the next lecture you will learn also how to make some statistical tests about the difference. Okay, so let's start with calculating confidence intervals for individual rivers, confidence interval for mean values. Okay, well, we will use both approaches, the manual approach like we did in the lecture, and then we will use a special function that does everything for us, and then we will compare how big the difference is. Well, first of all, let's define the confidence level that we need to use. Confidence level. Let's use 95, and then we will change it in a minute. Then let's define alpha, which is 1 minus confidence level divided to 100. And then the left tail is alpha half, the right tail is 1 minus alpha half. Okay, so we can get a t value by using the quantile function for t distribution. Okay, then we provide the alpha. For example, if we provide alpha half, it will be negative. It will let's just do it. Okay, so let's call it t left. Okay, and then degrees of freedom. We know that we have 10 values, n is equal to 10, so we have 9 degrees of freedom. And then we can do it for the same for the right. The t for the right, in this case it's 1 minus alpha half. Okay, then we will show both t left and t right. Okay, so let's see. So this is the left value, this is the right value. Because the distribution is symmetric, they are the same, the only difference is in sign. So we should have 2.26 standard errors from the average to get 95% confidence interval using 10 values in this case, right? You remember that for normal distribution it's 196, so in this case the confidence interval will be slightly larger. Okay, now we can just do the calculations, and because we have everything already in vectors, we can easily calculate the left and right boundaries for both rivers together. So I will just use BL, the boundary for the left, it's m minus t times standard deviation divided to square root of 10, right? So we have 10 values here. So this is our standard error. Altogether, this is our error margin, right? Then I will do the same for the right part. BR, and then it's plus. Okay. Then I can show these two values together. Show B left and show B right. Okay. So let's do that. Let me see. I need to, let me use the t value is t right because it's positive. Now I will be able to calculate. So these are the confidence intervals. This is for VADA, the smallest possible value is the largest possible value, and this is for RIBA, the smallest possible value is the largest possible value for 95% confidence. What you can actually do, you can combine these two together. So I will just use a function cbind that combines together two vectors by column wise. Okay, so B left and B right. Then I can add names, row names. I know that the first will be the first row in this case will be the VADA, and the second row will be RIBA. So I just add names, VADA, then RIBA. Then I know that the first column is the lowest, the left boundary, and the right column is the right boundary. So left and right. And then I'll show the confidence intervals as one data frame. In this case, it will be a metric. So you can see that for VADA, we have between 145.5 and 158.8. And for RIBA, we have 132.1 and 146.4. We can also round it if necessary. Okay. So this is a long way to calculate confidence intervals, but it's the straightforward way. So you see how how every step is carried out. Okay. Actually, you can do the same by using a very simple function which is called t-test. We will learn what t-test is soon. It will be in the next lecture, but so far we will use this t-test because one of the outcomes of this t-test is exactly the confidence interval. Okay, so so I will use this again, R1 for VADA. Just write t-test, and data $vade. Let's see what it shows us. Okay, so you can see that data, not dot, data. So you can see that this is the, it gives you a lot of different information. For example, some degrees of freedom, p-value, we will learn it later. But it also gives you the 95% confidence interval, which is this one, 144, 145.5, and then 158.8. And if you compare with the ones we have calculated manually, it's exactly the same. It's exactly the same. Okay. Then you can do the same for Vade. For Ribe, sorry. Ribe, and then show the second results, and you will see that again we have, this is the confidence interval, 95% confidence interval, and if you go up and compare it with what we had before, this is exactly the same. This is exactly the same. Okay. Then if you want to change the confidence level, you can just specify this conf level. The parameter is called conf level, and it's in a ratio of 1, so you have to take your confidence level and divide to 100. So in this case we got the same because we didn't change it. It's still 95%, but give me a minute, I will show you how to change it. Okay, so now we can change it to 99%, for example, and then I will use source to run the whole code. Then you can see that for 99%, the confidence interval is much wider. You can see 129, 149 for Ribe, and then it's 142, 161 for Vade. So if you want to have to be 99% sure that the true confidence interval for the population is inside, that's the price for that. Your confidence interval will be larger. Okay. Now the next thing is that how to show confidence intervals graphically. I told you already that I have written a function for you which is called error bar r. So let's use the function error bar for confidence intervals. Well, first of all, you need to get this function from either Moodle or the EDX, and it's just the file error bar r. So you have to have it in the same folder. I already have it here. I already have downloaded. This is the file error bar r. Because it's not a package, you need to load the code from this file to the memory. Okay. So the first thing you need to do is to write source, and then error bar r. Error bar r. Look what happened if I run this. I got a new section in my environment which is called functions, and then I've got a function error bar with all the parameters here. Okay. Now, what do you need to provide? You need to provide 3 main arguments. It's x values, y values, and the size of the interval. So the error, the half of the interval, this error margin. Okay. Let's calculate error margin first. It's a very simple thing. It's t times s over square root of t of 10, right? So this is our error margin. So this is the, you can see this is the value. So it's 9.56 for Vade and 10.23 for vice versa. It's Vade and Ribe, because Ribe has slightly larger standard deviation. That's why error bar will be larger as well. Now we can call this function like this, error bar. Then for x I will just use 1 and 2. So it means the first river and the second river. For y I will use our average values, and then I will use this e as error margin. Let's see what it gets. So this is the error bar. So you can see the real average value, and this is the uncertainty. Okay, so this is how big the variation of your average values are. Okay, and then you can see that actually this is about 144, and this is about 162, and it's, you remember, the big overlapping is because we have 99% interval here. Okay. You can also change colors and everything you want to change, and you can also make it as a bar plot. So I will just use the same M and E, but type equal to H. It means makes it as a bar plot. So that's how it looks with a bar plot. So you can see the absolute value here, and then you can see the deviation. Okay, so how big the uncertainty is. If you want, you can add labels to the groups. Like in my case, I will just use the column names. It's easier, column names for my data. It's exactly Ribe and Vade. Now you see the labels. So the first is Vade and the second is Ribe. Okay, so and then I recommend you to look at the code. It's just an R script. You can look at the code and see different parameters, how to change different colors and other settings.